Viscosity is the internal friction present in fluids. When one layer of fluid slides over another, the resistance offered is called viscous force. The coefficient of viscosity, denoted by eta, is defined by the relation F equals eta at dV by dy. Here, F is the viscous force, A is the area of the layer, dV by dy is the velocity gradient, and eta is viscosity. Its unit is Pascal second in C and Poiseuille in CGS. When a fluid flows, the layer touching the surface is at zero velocity, known as the no-slip condition, and layers farther away move faster. This continuous variation of velocity gives rise to viscosity. Fluids are categorized into Newtonian and non-Newtonian types. Newtonian fluids obey the linear relation F is proportional to dV by dy. Examples include water, air, and oils. Non-Newtonian fluids, like blood, toothpaste, and paints, do not obey this linear relation. At low speeds, the drag on small spherical bodies is dominated by viscous drag. Overall drag depends on fluid density, fluid viscosity, the shape of the object, and its velocity. For a sphere of radius are moving slowly in a viscous fluid, Stokes' law states that the drag force is equal to 6 pi eta RV. This law is valid only when the flow is laminar. The Reynolds number is small, the sphere is small, and its speed is low. G often tests incorrect applications, as this law fails in turbulence. When a sphere is dropped in a viscous medium, three forces act: weight, buoyant force, and viscous drag. At terminal velocity, these forces balance, leading to the equation mg minus v rho g minus 6 pi eta r Viscosity equals 0. For a sphere, the terminal velocity Viscosity is given by 2r squared times the difference in densities times g, all divided by 9 eta. Key insights include: a larger radius leads to a higher terminal velocity, higher viscosity results in lower terminal velocity, and a greater density difference means faster settling. For streamlined flow through a tube of radius r and length L, Poiseuille's law gives the volume flow rate Q as pi r to the power of 4 times delta P, all divided by 8 eta L. A key highlight is that the radius is to the 4th power, meaning the smallest change in radius drastically changes the flow. This law forms the basis of blood flow analysis. The Reynolds number, Re, helps classify flow as laminar or turbulent. It is calculated as rho BL divided by eta. If Re is less than 1000, the flow is laminar. Between 1000 and 2000, it's transitional, and above 2000, it's turbulent. Both Poiseuille's and Stokes' laws only apply to laminar flow. G applications include determining terminal velocity, calculating viscous force, solving capillary tube problems, and understanding parachute motion and blood flow.